Hey there, it's Shannon Mathchick Myers. Today we'll be taking a look at a Calculus 3 example. So here we go. The top of a rubber bushing designed to absorb vibrations in an automobile is the surface of revolution generated by revolving the curve z equals 1/2 y squared plus 3 for y between 0 and 3 inclusive in the yz plane about the z-axis. So we want to find an equation for the surface of revolution first. When we isolate y, what will happen is, we're isolating z, so we just get 1/2 times y squared plus 3. Here we go. Well, that's not very helpful. Let's take a look at the scale. All right, x is going to vary. It's not in this equation, so I'm not going to worry about that so much. Let's take y from 0 to 3. And then for our z, we'll go from -1. And then if you notice, if y was equal to 3 and you plug that into the equation, you'd get, I think, what is it? 9, you get 7.5. So I'm going to go ahead and take y up to 8. And then over here for lower z clip, we'll say -1. Upper z clip, we shall say 8. Got a pretty good picture of what's going on. Just so we have a little bit more wiggle room here, why don't we put x from -4 to 4. We can go ahead and we can take a look at the grid lines. So why don't we show the YZ grid lines, and let's take off the box. Sometimes the box can get a little bit distracting. We want to show those axes and ticks and labels, and the grid color is fine. So I think we're good to go. So this is what the graph will look like before revolving about the axis. Well, think about revolving about the z-axis. So we would have a revolution on the z-axis. So basically, if you were to revolve just any given point, you would have a circle, right, for our xy plane, would we not? We'd be doing this circle about the xy plane, but it doesn't end up being a circle because your values in your graph would change. So what it would look like at the end, once everything is done, and I'm just kind of trying to explain to you why the formula is what it is, you end up, when you're revolving about the z-axis, you have x squared plus y squared. Okay, and that's equal to this radius of the circle squared. So call it r in terms of z, that quantity squared. Because notice that as y tends from 0 to 3, the values for z in the original here change. Groovy? So now what is r of z? Well, let's check it out. And by the way, what it would look like is this. So we can go back to our handy dandy little grapher, CalcPlot 3D, lovely, it's free. And then we would end up, if you isolate z, you're going to end up having, we'll keep that one the same, you're going to end up having, and I can show you this work in a moment, but you would end up having this here, 0.5 times all this. And this, of course, is and we're looking at it, or as y tends from 0 to 3. If you wanted to get the full solid, you can look at -3 to 3 for y, because once we have revolved it, you get the circular one. So if we take off this picture, this is our solid right here. our ending picture will be the second one here. That's after revolving. Well, what is R of Z going to be? R of Z basically means Y equals, because we're in the YZ plane. So R at Z would equal to Y. Well, up here we have that Z is equal to 1/2 Y squared plus 3. So we want to isolate Y. So in order to do this, what would we have? Well, we would have Z minus 3 is equal to 1/2 Y squared. And then multiplying by 2, we would have what? 2Z minus 6 is equal to Y squared. And so that would leave us with Y is equal to, Y is positive, so we would say the positive root of 2Z minus 6. I'm going to go ahead and do this nice trick where I can move my writing down. So this is all sort of side work. All right. So now we will have x squared plus y squared would equal to R at Z, which remember is Y, the quantity squared. So the square root of 2Z minus 6 squared. So Y is R at Z and happens to be this value here, the square root of 2Z minus 6. So coming back, we would just have x squared plus y squared is equal to 2Z minus 6. And making it look pretty, that would give us x squared plus y squared minus 2Z plus 6 is equal to 0. Now, when I plugged in the equation for the second graph, I isolated Z. All right, so in order to graph this one here, I basically isolated Z, getting that Z was equal to 1/2, so I wrote it as 0.5 times x squared plus y squared plus 6. Groovy? Okay. All right, and so this here, just so you know, was a graph of the original one. So on this one here, we had Z was equal to what we were given originally, which was 0.5 y squared plus 3. Cool, cool? All right, so the end result for this particular part of the problem is this right here. And now let's look at part B. So now we're given that all these measurements are in centimeters and the bushing is set on the XY plane. Now we go back to our original situation where we have this equation here. Z is 1/2 y squared plus 3. But now what they want us to do is set this in the XY plane. And so the y value becomes the dependent variable and the x value becomes the independent variable. I think that the reason why they did this was just so that you didn't get confused about the shell method doing it in the YZ plane. And my apologies, but in WebAssign there is a mistake in this problem. Lovely, isn't it? So remember from before, our explanatory variable went from 0 to 3. So x is going to be going from 0 to 3. And that means that y, in turn, if you were to plug in those values, right, y would be going from 3, right, because if you plug in 0 for x, y would be 3, would be less than or equal to y, which would in turn be less than or equal to, if you plug 3 in for x, we're going to end up getting 7.5, right? Or what would that be? That would be 9 halves plus, that'd be 15 halves, which is 7.5, right? So basically what will happen is you'll have a graph that looks sort of like this. So again, you have the ordered pair when x is 0, y is 3. And we also have when x is 3, y is 15 halves, which is 7.5. So about here. And remember this shape, if you need to get a value in between, when x is 2, what would we get? That'd be 4 halves. So we get 2, 5, I think. So 7, 6, 5, and 2. So we get, this one is our bottom graph. But remember, you know, y is bound between these values here. So it's bound between, if we made our little deal, you'd be bound between the line y equals 15 halves and between this one here, which is x is equal to 0, and then this one here, which gave us, you know, right here, that is our x is 3, right? Because what happens is you end up having these, the rectangles, when you do the shell method, are going to be parallel to the axis of rotation, which would end up being the y-axis there. And so here, what you're looking for is the distance between the axis, so r of x is the distance between the axis of the rectangle at any given time and the axis of rotation. So do you see at any given time, this distance would just be, this distance here would be x. Cool so far? But the other distance here that's going to be 15 halves minus what that purple graph is. And that purple graph was beautiful. 1/2 x squared plus 3. Cool so far? And so you could call that the second y equals. Groovy? And that gives you this height here, which they call this whole thing, they call h in terms of x. And then this other one is called, so this other distance here is called r of x. So there we go. We've got it set up in general. Sorry if it looks a little bit messy, but basically what's going to happen is this. The volume will be equal to, so for the shell method, you end up having 2 pi times the integral from a to b of r at x times h at x, and then we're going to get of course, dx. This is our shell method. So we will end up with, sorry, spacing out here. We will end up with this volume, plugging it in, will be 2 pi integral from 0 to 3, because that is where x is going, 0 to 3. And then we'll have r of x, which was beautiful, so easy it's hard, was that x. H of x was the 15 halves minus 1/2 x squared plus 3 dx. So then we'll have, I'm going to go ahead and move this one down. I love technology. So then, working through it, let's see what we get. X will be equal to 2 pi times the integral from 0, to 3 of 15 halves times x. And then, so I'm going to be distributing that x through. So that would give us minus 1/2 x cubed, and then minus 3x dx. Simplifying, we'd get 2 pi times the integral from 0 to 3 of 15 halves x minus 6/2 x would be, I think, 9/2 x minus 1/2 x cubed dx. So our volume would be 2 pi times. So integrating, we would get 9/4 x squared minus 1/6 x, nope, it would be 1/8 x to the 4th, and that's going from x is 0 to x is 3. So the volume would be 2 pi times, do you see the lower limit, x is 0, would just 0 out. So plugging in 3, that would give us 3 squared is 9. 9 times 9 is 81. So we'd have 81 quarters minus 3 to the 4th would be 81. So 81/8. And then bringing, well, we'll get a common denominator. So our volume would be 2 pi times 162 minus 81 over 8. And then simplifying, we would get pi over 4 times 81. So our volume would be 81 pi over 4, and that would be in centimeters cubed. Cool, cool? All right. So next up, it changes a bit. It says the bushing has a hole of diameter 1 centimeter. So that means that in this image, we're going to have to adapt for 1 centimeter. But remember, you have to consider just half of that because you're going to be rotating around. So let me do a cleaner drawing for this one. So you'd have something like this. So if this is 1, 2, 3, and -1, -2, -3, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So y. And then remember, we graphed this earlier, so we had an ordered pair at 0, 3, and then at 2, 5, and then at 3, 7.5. So your graph would look something like that. That is your original graph. We'll have to adapt it just a little bit. And then now think about it. So remember 7.5, it was also bound here. But let's think about this, because we want this, so when it kind of mirrors over here, it would look kind of like this, right? And so we want a hole that has a diameter of 1. And so do you see that you have to start X at 1/2, all right? That would be 1/2 right here, because when it is rotated, you would have a hole like this. The measure here would have a diameter of 1. Does that make sense? So what's going to happen is this. Your actual shape that you're working with is what I've outlined here in green. And that allows for our hole. And so our rectangle, like usual, will look like this. Okay? Now, again, what's going to happen here is we are going to need to go from, instead of going from X is 0 to 3, X is just going to tend from what? Beautiful. 1/2 to 3. And everything else is going to be the same. So let's check it out. We'll end up with this volume will be the integral, because remember it is rotating again about that axis. So we'll have the integral from 1/2 to 3 on our X. Again, at any given time, you'll be X units away from the axis of rotation. And then our height of our rectangle, right, is going to end up being 1/2 X squared. Was it plus 3? I think it was plus 3. Yep. And then dx. So we're going to get, GC will get the same antiderivative. So, and then, sorry, we have a 2 pi here. So assuming I did that correct, we will end up with 9/4 X squared minus 1/8 X to the 4th. And that will then go from X is 1/2 to X is 3. And so, be a little more complicated. We will have our upper limit of integration, again, would be 81/4 minus 81/8. Our lower limit will now be, let's see, 1/2 squared is 1/4. And so we would get 9/16. And then, let's see, minus, so we have to do 8 times 16. And so we would get, I believe, 128 as the denominator, and then 1 in the numerator. And then continuing, we would have 2 pi times, we did this calculation before, we end up getting 81/8 minus, let's see, we'd have to do 16 times 8. So that'd be 72 minus 1. So that'd be minus 71 over 128. And then, let's see, I mean, really, you'd probably do this on the calculator. But since I started the common denominator, I shall finish, I promise. So let's see, the common denominator would be 8 times 16, right? So we would have 81 times 16 is 1296. So we would have volume is 2 pi times 1296 minus 71 all over 128. Almost done. Notice we can divide out that 2. We'll get 64 in the denominator. And then, did I forget my pi in the other one? Nope, I'm good. And so then we'll have, let's see, 6 minus 1 is 5. 9 minus 7 is 2. So we'd have 1225 over 64. And then times pi, centimeters cubed. So hopefully I did the arithmetic right. And I apologize for the error in WebAssign. Hopefully they'll have it fixed next time around. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please subscribe. Bye.